do the hard part and the first part of the Coulomb development that we haven't done so far. But we're going to compare it to the 2D oscillator. And there's some rather cool things which I've indicated here by a mystery similarity appears. And that's on Halloween is past, but we can have that for something to talk about today. In any case, the effective potentials, the stuff that we all have spent a lot of time on, are going to be featured, and so is our 3 steps from hell that we got when we did the review unit. Unit 1 had just a brief look at the outside of the sophomore physics Earth. Well, now we'll look at the inside of the sophomore physics Earth at the same time we look at the outside. So the two come together here in this development. Now, the idea is when we get done and really have a detailed orbital function for the Coulomb field, as well as the oscillator, and we're going to do it in polar coordinates. We didn't do that before. We were using Cartesian mostly there. We'll have some geometry to go with it. Particularly for the Coulomb, the geometry involves things that we didn't spend much time on that had to do with the polar coordinates view of an ellipse, hyperbola, or the dividing line between those two is a parabola. So all of that starts to come together over here. And then if we have time, we'll take on the details of that and a little bit of the geometry. Now what's coming next, and that's on Tuesday, the last class of Thanksgiving week, we're going to take an entirely different approach to the Coulomb that uses a vector called the Lens-Runge vector. I call it the eccentricity vector, which is probably what it should be named. It should be denoted as such. But anyway, that's a group theoretical approach to the solutions that we're going to be getting today.
So that's the Runge lens vector?
Yes.
Right.
And it's very important if you're going to be doing quantum mechanics of a Coulomb orbit. Okay, so I'm going to, as usual, try to keep these things more or less lined up with each other. This is the kinetic energy that we wrote down just using metric coefficients, and the idea of the radius rho here comes from having a constant m rho squared phi dot. That's the angular momentum. And so using that as a constant reduces the kinetic energy to this much to be added. This is the barrier, centrifugal barrier, to be added to the whatever potential you're going to put on this thing. And you can do some really interesting mechanics with other things than the oscillator and the Coulomb, but they're sort of at the opposite ends of a set of possibilities. So at this point, we're talking about a mathematics that would work for all central forces, that is, all isotropic, things that are only functions of the radius and not of the two polar angles. And then the total energy with these together makes use of the conserved quantities and the parameters, of course. That's the conserved quantity that's key to this particular development and anything like it with an isotropic potential. And here we go with the oscillator again. In this case, the potential is just the good old radius squared times the spring constant over 2. And looks like that. We've played with this thing, and this is on the web, right, where you can move up and down and around and watch the oscillations that come with the sophomore physics inside of Earth. This is outside, where I've replaced the k rho squared with another constant. We have to be careful about what's the sign of that. Because if I make that sign so that I'm only dealing with a repulsive thing, we're not going to get any orbits that are closed, but we'll be getting weird scattering orbits, and that's going to be part of the next few days, going through that physics. In any case, this plot shows negative values of the potential, that is minus k rho. That's attractive. And this is true for positive k. I have an explicit minus sign there. Okay. So we're dealing with the attractive side of Coulomb orbital mechanics here, and to do that, I have an explicit minus sign. So k itself is positive. Now, as soon as you make k negative, well, that's going to be a different kind of orbit. It's going to be an orbit that does not stick around ever. Okay, so bound orbits E less than 0, unbound orbits E greater than 0. Oscillator goes forever. Everything's bound there. But this is more complicated. Okay, in either case, if k goes negative, blows up. And k going negative here means that you, instead of having a potential well, you got a barrier, right? And you just fall off. Like that problem that I gave you in one-dimension parabola. And I think that's just all that I've said already, okay? Explicit minus conventions hiding under the word there. Okay, let's get started. I'll put all of this stuff to look at, and we'll go further here. Just to remind you of what we did in Unit 1. Okay? In Unit 1, we put them together, the oscillator and the Coulomb, potential and force, okay? And the force comes down here nicely, tracking like it did with the potential, and then all of a sudden goes up here. So inside the Earth it's just constant k times rho's, just a Hooke's force law, k times the radius. Okay, and it's come back to 0 right here, and then this is symmetric on the other side. But meanwhile, potential down here, and remember there were 3 steps to go from sitting at the center of the Earth. Okay, you climb up the stairs to be sitting on the surface of the Earth, and then you, by another step, you apply yourself some kinetic energy in order to get into a circular orbit. That takes you to this level. And then you use the same amount of energy, number 3 step, to go to infinity. So as I say, it's the 3 steps to heaven, but coming the other way is 3 steps to hell. It certainly is a pretty good representation of hell at the center of this particular diagram. Okay, so these are all things we've got, and this is a little bit of a simulation we looked at a little bit. Now we're going to look at the details of that. Okay, so here they are sitting side by side. Okay, good old oscillator, good old Coulomb. And one of the things that you look for first in these effective potentials is a place to sit, a place where you can sit. Okay, bottoms of a curve, depending on what parameters, values you have. And in this case, you can crank the parameters up as much as you want, as long as you don't change the sign of k, and you'll always have a place to sit. Not so here. This one you keep cranking up, and pretty soon your place to sit goes to infinity, and then from there on out it's totally repulsive. We're just talking about the centrifugal barrier dominating. And then if you change the sign of k, it's even worse in terms of boundedness. So, we look for the radius by solving for the derivative of the effective potential being 0. Okay, so we come up with a stable a place on this one, and this is something we didn't work out before. At least I don't remember us doing that, where I would get the stable radius in terms of the angular momentum of the orbit and the Coulomb constant in mass. So it's a square root of a square root with a mu sitting in the numerator of the first square root. So we square that thing, and we can write a fourth power law here for those values. Over here, you solve for this thing. Okay, same deal. Take the derivative of the effective potential, that's this thing, and set it equal to 0, looking for a place to sit. And you get something that looks like this. Now this one gives you a mu squared over mk. This one gives you the radical, you see. If I square that, then I have mu over the square root of mk, okay? This one's just giving you mu squared over mk. So there's a big difference right there. Okay. The equation here is equivalent to this one, where you're balancing centrifugal force and the attraction. Okay. Next thing is to take the second derivative of the effective potential and get an oscillation frequency around that place to sit. And for these two, this isn't just an approximation. This is exact. It turns out that this is exact. If you work this out, you get something that we'll later show is an exact relation for that frequency. Because that frequency is part of the elliptical orbit here, and it is going to happen with the Coulomb as well. Okay, so these are the steps that make use of an effective potential, but in this particular case, not just an approximation. I don't have to go on and do higher derivatives and make a Taylor series here. This is it. There's nothing more that you need to say. So once again, here we just get the frequency k over m, harmonic oscillator. It's got a factor of 2 because this thing goes in and out, and then in and out again, and then it's home again, you see. So there's going to be that factor of 2 that this one doesn't have. But then this is an entirely different relationship of k's and mass, okay? I'm sorry, k's and mass and angular momentum. This one doesn't care about angular momentum. It's not a function of it. And those are issues that we want to compare when we get to the end of this, but I can show you that much right now. Okay, and let's see what else. Oh yes, compare the orbital frequency of this particular thing right here, the orbital frequency that comes for that one, and this is annoying to have this little edge of screen here. I've been writing, and here's the angular orbital frequency for this particular fellow here. Now, the result of this is that you will get a 2-to-1 relationship, which is, we talked about that before. So, you know, do too much with that, except to move it ahead here so that it's showing on this one where we can read it better. Okay, so compare angular orbital frequency here to the omega of the in and out motion on the radius, okay? And that's a 2-to-1. Compare the angular orbital frequency here to the in and out radial frequency, and you see it's 1-to-1. So the ellipse that we're going to make here is starts high, goes low, and then comes back to high. That's one orbit. This one starts high, goes low, and then goes high again. Now you're halfway, then it goes low again, and then comes high. So you go apogee, perigee, perigee. With this oscillator, this orbiter, it's going to be an ellipse that's off-center. This is an ellipse that's on-center. Okay, we've talked about that before, so I think we can go on here. Now, okay, so we've got everything that's around the bottom of one of these effective potentials, except the ends, the classical turning points. That's what we need to finish this. Need the classical turning points. And I say classical turning points, this is classical mechanics, obviously we're interested in them, but so are you when you do quantum mechanics. You're interested in places where the wave function goes from a wiggly thing to an evanescent exponential thing. It will be, the inflection point will be right at these points. So that's why it's interesting. So if you have this much energy, they're your classical turning points. So you're going to have a wave function that's evanescing here and then goes like this in the radius and then dies off outside of that region. Here you have little wiggles, whatever the energy will let you have, and then it dies off outside of that region. So one of the things we try to do here is make connection with the quantum world whenever possible. Okay, so classical turning points. Now we got to solve the quadratic equation, and that's true for both of these things. Here the solutions have some things that are really in common, and they have some mysterious things that are in common that I'll try to point out. But we're just cleaning up the equation here. We have a rho to the fourth, and we have a rho squared, and we have a constant. So this is a quadratic equation in rho squared, or 1 over rho squared, and that's what you want to look at. You can solve this equation for 1 over rho squared by itself and constant, or you can solve this one. Okay, both have some advantages and insight for us. Over here, you do 2, only this time it's 1 over rho and a rho. Okay, those are your two choices for getting the classical turning points. Well, the answer for this one is this for doing it with rho, and this for doing it with inverse rho. Okay, both of those things are quite useful. And since it's there is this weird similarity, which the purple arrows are trying to indicate here. And I think once again we will go ahead on this particular screen here and make use of the fact that the screen's bigger. So what I'm wanting you to notice is a mysterious similarity. A similarity which sometimes does a plus sign, sometimes does a minus sign, but basically you're replacing the K here with 2E here, okay? So wherever you see a K on this side of the world, that's the oscillator side, you replace it with 2E over there. And wherever you see an E, you replace it with a K. Okay? Okay. It's kind of neat, kind of weird. E goes to K, K goes to 2E. Okay. Mysterious similarity. Okay. Now, I'm checking on this in the literature. The best I can find is this is called the Kustenheimer-Stifel connection. The idea that you map the eigenvalues, the energy, and they're talking about quantum mechanical situation. Okay, they skip the classical completely. You're connecting the eigenvalues of one type of problem with the coupling constant for the other one, and vice versa. I have very little to say about this. I looked at Kustenheimer-Stifel, very mathematical sort of stuff, and it didn't seem to go anywhere, but maybe on second look, we've come up with something. But I wanted you to see this. This is, more than you would get in any of the classical mechanics books on the bookshelf over there. So, next stop here, I'll leave that out for a moment. The next stop here is to actually solve the equations that go with anisotropic harmonic and Coulomb. Just rewriting these quadratic equations, but just rewriting the rho dot that we get. The one thing that helps to do this is to go ahead and take the derivative of the phi with respect to radius and put the time dependence in there, and then get an equation that looks like that, and that's something that can be rewritten that way. And that's true for both of them, because this is just talking about angular momentum here. They're both conserving angular momentum, and they get to do this, regardless of what their radial stuff is. So we have a rho dot equation now, okay, that we can solve. It's a differential equation that's going to yield something as a function of time for the radius. And here's the story for the oscillator, and here's the story for the Coulomb. Now you can go and check yourself with some of this, and that will happen in a little bit here, but that K to E thing is going to re-emerge for a few more steps here. This is where we take this little relation right here and get an equation which we really want, and that's the configuration space equation. We would like to get time out of the place for now and see if we can come up with a closed form expression for rho in terms of phi, and it looks good because that's the kind of integral you can do, although this rho squared looks suspicious, so does this one, but it turns out it's just what the doctor ordered. So here we go, at least in a beginning of the thing, and you have equations here that look pretty similar. This one inverse rho, this one rho up, rho down. This is the angular momentum contribution. That goes away with mu equals 0, but that's very simple motion, straight in the radius and back out again. We're looking for something that goes with a moving phi. Okay. So, first thing to try, since we've already mentioned that we can do 1 over rho or we can do rho, let's call 1 over rho u, and this is very common notation. This is pretty much standard stuff for a little while here in every classical book I know of that does the Coulomb. We don't always do the oscillator this way, but when the Coulomb comes up, it really helps to turn that over so you make something that's easier to solve. And here and here, we're looking at something that, well, this one's got, this term is the same. This is very different right here. You've got a u squared in the denominator, you've got a simple u there. You've got this term is the same. And then we have to look at, if we're going to do 1 over rho, then u squared is 1 over rho squared. That's what we're actually dealing with right here. And that means then that you can make a variable change right there if you just let x equal u squared. So it's one more change of variable to get equations that will be integrable by some nice formulas. Now, let's see if I've got anything I can say. The mysterious e to k and k to 2e is not something that survives at this point. And I guess that's to be expected because they're very different ellipses, centered, not centered. But anyway, it's equations that we could deal with fairly nicely. Now let's go on and take a head on that screen over there so we can use the bottom few inches here. And that's the stopping point right there. So these are the equations that we're going to just do a single formula for these. And this is the deal right here. Both of these equations, the actual orbital configuration equation, can be gotten by just simply writing a formula for this interval. And that means you have to get this thing into the form of a constant plus z, some variable squared. And so that's what we do. We actually look for the roots of this polynomial and then write them out precisely that way. This minus sign turns that thing into z plus minus z, and then this is z minus z minus. Now these are the classical turning points. That's what we're after. We want to do an integral between those points to see our orbit. So our orbit isn't going to, if it's classical, it's not going to go outside of it. It's quantum mechanics that lets you evanesce outside of the classical region. So the roots of this thing, as it says here, perigee, and then apogee. Remember, apogee stands for up, so that's C plus, and this is the other thing, which is going to be less than this thing. Okay. And it's just a question of rewriting that thing in a simple way so that I can give you Z plus and minus, and then give you alpha and beta. And then, of course, once you have that, you can write that equation there, and that's the kind of integral you know, a constant and then a variable squared. And I think that pretty well takes care of it. So we're going to use those formulas right there. This is something we'll call beta. We'll call alpha, because that is what works. Here it's a little different. And anyway, this is phi of z, this is z of phi. And phi of z is what we started with here. So, but we're ending up here with z as a function of phi. Z is radius, okay? We're going to be seeing some sort of orbit like that, or maybe one that curves in like that. Obviously, for this problem, the oscillator problem, it'll curve this way, but this is just a sketch. All right. Now, let's see if that's, yeah, that's the end of that. So let me go ahead and move this up to that position. There's a radial polar orbital function, and now we've got a go forward with that. Okay. Now we're going to start to get the basic geometry. What we're after is the geometry of the orbits that come out of this, because all of this algebra is not something you want to go through every time you change something. The basic idea is to just look at this equation here and replace the A, B, and C with whatever you see up here. Okay, so for this connection right here, there's the K going to 2E. There's an E going to K. Okay, and then this stuff, the angular momentum stuff, just goes to itself. There's a minus sign on both of them. So pretty much the same deal for both of them, except that I make different substitutions, A, B, C, and D, for these two. Okay. This one's mu squared over m squared. That's the same. But this one right here, the B, is 2e here with a minus sign and 2k without it. Then the next one here is a k and a 2e with a minus sign. And then, well, the d's, there's an extra 2. Okay. And at first when you do this way, you say, wait a minute, I got an extra 2, I have an extra 2. I must have made a mistake. No, that really belongs there. So, now we can evaluate the alpha, which in terms of well, it needs to know B, A, B, and C to get that one. But this one right here, pretty easy. Okay, there's the alpha and the beta in terms of actual physical variables. And the algebraic details are on the following pages, but that's at least a start, and those are the things that you use to get your apogee and perigee, the turning points. And here, this I say algebraic details on the next page here, let's just take a glance at what those are. I'm just rewriting those things out and putting some pieces together for that. Okay, so I'll do the algebra stuff over here, and then we'll continue with this. So this is the detailed orbital functions, actually. Pictures of them from the simulations. Here's our nice little symmetrically placed oscillator orbit. And here's the one that's off, has a perigee. and an apogee, and that's it. This one has 2 apogees and 2 perigees, right? Okay, and this is making a connection here between these two. You say, this is the effective potential, radial, okay? The thing that's going to be moving, all right, as this orbit happens, but this at least connects it up. Then the same thing for this one, a little more squirrely. In fact, it has a nice dip in it because this thing is going so much slower here than it is here to keep the momentum constant. It's true of this one too, but that's extreme. And when we do the geometrical, group theoretical, I could call it, way of solving all of this in just a few lines, you're going to see by the geometry how different. But of course, you've already seen that when we played the orbits, that had this thing go and jerk and then drifting along like that. So that is very different from this much more smooth thing. But one of the things that you see here is you do get similar equations in terms of a bunch of constants, plus or minus sign, some other constants, and a cosine. Well, this one pretty much the same, except it's cosine 2 phi. That 2 really needs to be there because of this one being 2 ups and 2 downs, right? No, it's only a single up and a single down, okay? But those are the solutions right there. This is not an equation we wrote before. We did everything with Cartesian. Makes sense for the isotropic centered oscillator, right? The geometry is similar, simple for this, really simple. This is a more complicated one based on that Brings Lunga or Lunga-Renz or whoever. It's actually somebody wrote out all the names: Laplace, Legendre, some people I don't even remember, then Lenz, and then Runge, and even Hamilton, right? Seems like everybody discovered that thing that we're going to talk about later. But they didn't really use it. That's the thing that's kind of interesting. There's so many things that we can do in addition to that. Anyway, this particular one, as I say, is discussed shortly. This is one of, as I say, one of many equations of focus-centered ellipse. And this is one of many equations of center-centered ellipse. And we're going to discuss a number of those. So that's it. There's the K becoming 2E. Okay. Got an E here that becomes a minus K. So that thing that had the purple line connection is all the way to the end. This is the end now. We've got the equation. Now notice also this is 1 over rho squared. This is just 1 over rho. Okay. So really 1 over rho is the square root of this whole thing. This thing right here. Didn't point that out before, but I make sure I do. Okay? So far so good. Now we can't go too much longer or we're going to hurt our seminar. So I'm going to sort of breeze through these just derived equations here. There they are. Okay? And note the things that you get that we really already had. Okay? There's the 2 alpha, which is rho plus rho minus. It's just K over E. Okay. There's the minus between them. That's 2A times the epsilon number, which we're going to be calling, it's going to be the eccentricity of the ellipse. This one also has a thing that we'll call epsilon. It's an ellipse after all. It should have an eccentricity assigned to it. Okay, so these are things to look at for when you're doing problems on this. You'll find easy solutions in that pile somewhere. But this I want to make sure we do. We'll do 5 more minutes here. Then we'll have 10 minutes to get ready for the seminar. All of the conics, every one of them, parabola, ellipse, hyperbola, attractive, hyperbola, repulsive, they all obey a very simple relationship involving polar coordinates. This is not something we talked about before. This is very powerful. Okay? And the basic idea is, and we did talk about the parabola having a directrix, right? This is all high school algebra, right? But the basic idea is if you're given this eccentricity, then this radius has to be matched with a length here that's r over that eccentricity. Now the eccentricity for an ellipse is less than 1. So this is always greater than this for an ellipse. But the thing I want you to get a feeling for is that this ellipse can grow, you see, to, you know, even go out the wall there and down to Fort Smith, right? And you still have an ellipse, but by this time it's looking very much like a parabola. Okay. Then what's funny is you let it go past Fort Smith, the universe, out to the galaxies, and come back on this side, okay? And then you have hyperbolas meeting each other. So you got to imagine the ellipse going out around the globe, or some kind of globe, and this thing right here coming in and hitting you in the butt. Okay? And halfway between those two cases is the parabola. It's a single boundary between the ellipse, eccentricity less than 1, and eccentricity greater than 1. Eccentricity equal to 1 is the parabola, and that was the definition we talked about before. Right? So, in the short period we have here, that's the really important thing. Then it's just a question of using that geometry. Okay, this r equal epsilon, okay, is equal to, and you just add up what you've got here. Okay. Got this r over epsilon. Well, it's a sum of r cosine of phi, and then this distance right here, and remember the thing that was called the lattice rectum, right? And we changed that to, you know, not infringe on the copyright of the Roid Rage Gym in Ventura County, or Venice Beach, okay? And so this is the lattice radius. And all conics have this. A parabola had it, right? Just above the focus, how far are you? Okay? That's a very important quantity, right? Well, your distance to directrix has to just be like this. It has to be lambda over epsilon, okay? So that goes right here. And now you have an equation that you can solve for r that's quite nice. And even nicer is this equation right here, where I just write the r immediately in terms of 1 minus epsilon cosine. See, there's r on both sides of the equation, so I get rid of that. Okay. And then 1 over r, we were working with 1 over rho, well, we mean 1 over r from now on, okay, in these things. You flip this thing over, you see you have 1 minus epsilon cosine phi divided by lambda. This is the geometry coming in there. Now back a few pages we had some relationships for 1 over r, so now we can start assigning the epsilons and stuff like that, the geometrical stuff, to energy and angular momentum. Those are the parameters of the physics that we need to do. Now part of this is to get the perihelion, that's the perigee radius, and the aphelion is this point right here, and the helion distance, that's really a name for distance. Those are flips of each other. 1 minus epsilon, that's a small a number here. This is a bigger number, so this is a smaller distance, okay? You get that just from this equation by cosine of 0 being 1 and cosine of pi being minus 1. And what else can we say? Well, we got the sum and difference of those things. That was interesting before, it still is. But this is the most important result if you just want to immediately do things with conic section. We could have just gone right to this one with closer steps. But the idea is that the total energy is a function of only A, only the major radius. It doesn't care about the minor radius, B. That's for angular momentum. But this is just all there is to it, and that's really powerful. And this minus sign has to be there for RK, which is positive when attractive. And our energy is negative. All the energies are negative when you're bound. It's only when you get above the escape energy that you then have positive energy. So these are relations here that get us the physics together so that we can make a table out of the parameters that we have. And I'm going to go ahead on this one to this point because that is really an important set of results there. Okay. So major radius, focal axis, lattice radius, not that awful word we used before. They're all now connected with the various physical things. So make a table right here. If you're just doing x, y parameters, that's Cartesian coordinates, okay? This could have been a lot easier than we did. The minor radius, B, has got angular momentum and energy and mass, but not the spring constant in it, okay? It's interesting to see the dependencies of things. Now the energy here is just got the spring constant and one orbital parameter, A, okay? The angular momentum here is pretty simple. It's got the Coulomb coupling thing, the mass, and here's the lattice radius, okay? That's angular momentum, mu, remember? Okay. Now eccentricity, it's a fairly complicated function of everything. The lattice radius, though, I mean, there's a nice relationship there, just involving the spring, I should say the Coulomb constant and mass. Okay. So this is a good thing, you know, that lets you deal with the complexity of all of this stuff that's behind the scenes. Okay. Now, when it comes to figuring out time, I'm going to zip through this, but remember we had this nice construction for the harmonic orbits, the ellipse that was centered, right? Where we just drew an arbitrary line that intersected the B circle, the thing that had a B radius, and also the A radius circle, okay? In other words, the apogee circle and the perigee circle, all right? And all we had to do was just draw that line and see where it intersected. Where it intersected the internal one, we drew a horizontal line, and where it intersected the vertical line coming down was a point on the orbit. So this line here goes at a constant angular velocity and drags this thing at a non-constant velocity. It starts out hardly moving at all toward the radius, toward the center, and then it starts to fall really fast right here as you drag that thing past this point. Then it zooms ahead on this side and to finally reach another apogee. But the perigee, everything's going really fast. Well, this thing does the same sort of thing. This thing right here, and that's something I'm just going to zip through it really fast. But this is Kepler's construction. This is a construction we sort of cooked out of. That I called it Kepler's construction, but I've never seen that in any of the things that Kepler is claimed to have discovered. But this very definitely is. And the derivation of that is just some algebra that's not terribly hard, that yields an equation for time, period. And then angular frequency. In other words, as I crank this thing uniformly, this thing is going to really jerk over. You can see from this construction that that's going to happen. And we'll see it better later on. Well, anyway, I think I'm going to stop right there. The rest of this stuff is just taking ellipses and hyperbolas and parabolas and things like that, and just going through for very specific values of the various constants, A and B and epsilon and lambda. This is the polar coordinates of an ellipse. This is the Cartesian coordinates of an ellipse. Or conic section, we do hyperbolas too. So these are all nice, beautiful pieces of geometry that you can play with on your own time.
Professor Harter?
Whenever you're interested in it.
Professor Harter?
There's the thing that...
I think we have 15 more minutes. The eats start at 3:30.
Well, that's right. Okay.
So we got time.
And if you've got some more battery on there, I was just looking at the clock. But yeah, okay, let's go ahead. This is the thing I was telling you about right here. Eccentricity 0 is circle. Eccentricity 6.65 is an ellipse that's clearly oblong, okay? Here's 0.85, okay? And then, finally, singular case, parabola only gets one value of epsilon, 1, okay? So that goes out and just keeps open to infinity, okay? Now you just make that epsilon 1.1 and you're liable to get hit in the butt by this thing. So there's the ellipse going out, right? But going out on an asymptote, okay? And then coming back, you see, right here. And that's already just with 1.35. So, you know, that's a kind of a cool thing to know. And all of these equations are matching that. And this is just another chance to connect up with lambda with this thing here in the epsilon, over lambda with this stuff here. So there's the cosine, there's the constant here. Now, hyperbola geometry, this is something I've drawn it this way because I want to do some geometry of scattering. Rutherford scattering. Rutherford's the guy that really opened up old-fashioned physics for modern physics to begin. And he's the one that discovered that if you put alpha particles toward gold atoms, that they flew as though the gold atom was an infinitesimal point. Now, he didn't have enough energy to really explore. He never got anywhere near alphas actually colliding with the nuclei of the gold. He was miles away on these scales, but he got close enough that people said, wait a minute, it should have started hitting it way, you know, at Fort Smith. Okay, now it's got all the way to here. It's still got a lot way to go because the nucleus is so damn small, right? Talking about femtometers, right? 10 to the minus 15 meters, 10 to the minus 13 centimeters. The Fermi, okay, unit is what we're talking about here. The atoms are all angstroms, 10 to the minus 10. Bohr diameter is 10 to the minus 10 of a hydrogen, which is a pretty small atom. Okay. Of course, it came through a lot of electrons, but that doesn't scatter alpha very extremely. And we're going to talk about that by setting up a coordinate system that's on the asymptote from the alpha beam. We're going to use this to make a really elegant picture of Rutherford scattering. And this was something that didn't exist until we did it in a class project at Georgia Tech. Actually, it was USC when I did that. So that ended up in the American Journal of Physics, and we'll look at that come next time, along with another paper that I wrote about the eccentricity, which also showed up in the American Journal of Physics. So it's kind of neat when you work on this stuff that's been studied for, you know, over 100 years and come up with something of observation that makes it easier to think about. Anyway, I just wanted to show you the geometry. This is a case here, 1 and 2, for the hyperbola. Okay, where is the A being measured? Where is the B being measured? Those are things we'll talk more about. But the B turns out to be an impact parameter for the scatter. That's what results here. And you can see that when you draw it this way. So here's the line that the alpha particle would have been on had there not been a repulsive nucleus that made it, first of all, deviate from that line and start to point away from that line, and then just as it gets really close to the nucleus, follow a hyperbola, then that's the closest approach. So that's what we'll be analyzing next time. Okay, same thing here. It's just another way to tip things. That's the game you play when you want to discover new stuff. You just try looking at all the different things. And by the way, the directrix, which used to be outside of the ellipse, well, it's outside of the ellipse still. It's just that the ellipse folded over, and then the directrixes look like they're going to run into each other. Okay, so those are, of course, then there's the interesting thing that the difference between these two radii from this focus and this focus is a constant, 2a, 2 times this major radius. Okay. Forget what I was trying to show here. I guess this is just going back and showing you how r over epsilon to the directrix goes with r. So it's a little different because you're going to sit in the fact you do with this one. This is an r prime over epsilon. That also has some interesting geometry. But just making that epsilon greater than 1, you see, has changed the thing tremendously. Yeah, those are the what you would call the perihelion and aphelion, but it's on a completely different curve as far as we're concerned. And that curve goes out on an asymptote. There's some other stuff that just shows the geometry that's present here. Now this is actually in the textbook. This is important because you have a geometrical series here of the epsilon. Here's b times epsilon, here's b divided by epsilon. And basically what you're doing is you're just drawing circles and lines to make, and there'd be another one here if you wanted to finish this thing. And if you kept doing this, you would have it b over epsilon squared and so on. The relationship between that series and the series with the major radius is important. This is with 3/4, this is with 4/3. This would be a hyperbola, this would be an ellipse, so they kind of look about the same. Anyway, you're talking about the geometry in this neighborhood around the focal point. And you're talking about how if you had a string that you let go while it was attached to the foci, it's the difference between these things that's a constant, not the sum. If you make the sum of the distances to the curves, then it goes the other way, makes an ellipse. Or if you have the string going here and then going to the directrix directly, you make a parabola. That's the singular case. But you can see that as I pull this thing out, I keep pulling more and more string out, but always maintaining the difference. So I built a device that had a little thing that let go. It was just a thing with string, it was a fishing line actually, wrapped around something that was connected to. So it would just unroll the string. You'd set the difference beforehand, and then just pull on a thing, and it made a hyperbola on an overhead projector. This is the amount of work I went to get demonstration, which, you know, it's sure easier to do that with HTML. But if we built this device that went on an overhead trajectory, and most of the time it would work, but you can imagine that it would get stuck and not be too impressive. But that was based on the eccentricity vector also. So if you want to read that, maybe that's where you find it out. Anyway, I remember the zigzags that we had before, and we just talked about basic power loss, right, and exponentials. Here it's happening again. And here are all of the equations collected, plus the thing, just to remind you about the Cartesian parameters, the physics, and the polar parameters. A and B for Cartesian, epsilon and lambda for polar. Okay, so we've looked at those formulas before. And the key to Rutherford scattering is to tip this. Just tip this and say, okay, I'm going to be talking about something coming in, and this is going to be the beam line, and going out. That's for repulsing. Okay, but it could also be that this this one is repelled by this one. This orbit here is repelled by this focus right here. Okay, so it's sort of a double thing. So just forget about this one if you're thinking about typical scattering. That is repulsive or else attractive to this. Okay, and Rutherford's problem was positive alpha particles hitting positive nuclei, so that is a repulsive thing. Now, what we're going to look at also are the envelopes that are associated with the scattering. Okay, I think that's all that we need. If you want to go back to any of the stuff that we skipped over, we'll do that. But I'm going to, well, this particular lecture ends right here, so as we go on to 26, we are done.